So we had actually, if you remember, started the second module that is on crude oil characterization. And I will just go through very briefly and do a recap of what we studied. We mentioned that we'll talk about how we characterize such a complex mixture called crude oil. And basically, the way we actually understand crude oil is in terms of how it distills, at what temperature, and the various other impurities which are present in that crude. And if you recall, I had mentioned that if you plot percentage versus temperature, percentage volume versus temperature. So as you go on heavier and heavier, this is the boiling point, 10 degrees Celsius on the x-axis. If you go up on temperature, the normal paraffins and the isoparaffins, they tend to start reducing. And depending upon the crude, if it's a heavy crude, you may not even get anything beyond 400, beyond 500 degrees. Monocycloparaffins like naphthalene, whether these are cyclopentenes or cyclohexanes, obviously these are alkylated, so they will also start reducing. But what takes off is in terms of polycycloparaffins, which are naphthenes, which is condensed ring naphthenes, two ring or three ring or multi ring. And then actually the mononuclear aromatics, these are like benzene derivatives, benzene, toluene, xylene, or higher alkylated aromatics. They actually start, they're there and they continue to be there right till the end. But then what takes off is a polynuclear aromatic. So ultimately, when you get to the end of the barrel, you have mostly polynuclear aromatics, which are mostly asphaltenes, resins, etc., and some amount of aromatics and saturates. And this graph, if you recall, was in terms of carbon number versus boiling point. And these lines, this line represents the normal paraffin. This line represents what you call as aromatics, naphthenes. And then this line represents aromatics, two-ring aromatics, etc. And as you can see that as you go from naphtha to vacuum residue, the complexity of the molecules increases to the extent that when you're in vacuum residue, you have high metal content, which is present in form of porphyrins. And this is essentially part of what we called as asphalt, which is roughly the heaviest, hydrocarbon present in crude oil. So it's a complex mixture, and as I mentioned, there is nobody in around the world who has ever actually analyzed each and every molecule in a crude oil. And so even if it's a light crude oil, there is no way you can actually determine each and every molecule. So there is no analytical technique which has been developed. And hence, in order to understand this complex organic mixture, we need to have some techniques. And that actually brought us to the discussion of how do we understand crude, and the way do we do it is by classifying crude oils. And there are four types of classifications, and they can also overlap. Like, for example, the origin of the crude oil. That actually almost tells us 80% of what that crude oil would be because of the experience of handling crudes from that region. The other is whether it's a light or a heavy crude, and if it's a light crude, we know it will have more paraffins, naphthenes, and alkyl aromatics. If it is heavy, then we know that it will have more polynuclear aromatics and asphaltenes. And also the nature of the crude, whether it is paraffinic or naphthenic or a mix between the two. And so, as I told you, like the crude oil that we are blessed with in our country, both from Assam as well as Bombay High. They are mostly paraffinic, but they're also aromatic. So they do have a significant quantity of paraffins and aromatics, but hardly anything in between, like naphthenes. And the fourth category is in terms of the sulfur level, whether it's a sweet or a sour crude. If it is a sweet crude, we call it as a low sulfur crude, we call it as a sweet crude, and high sulfur sour crude. And we came up with the first quantitative definition of crude oil in terms of density. and I introduced a kind of a parameter called API gravity, which is 141.5 upon density minus 131.5. And the way we classify crude oil in the industry is in terms of the values of API gravity. Anything greater than 30, 31, 35 would be a light crude oil. Anything lower than 20 is heavy crude. And then somewhere in between, we call it as a mixed crude or a kind of a blend. So this is API is a very important. API stands for American Petroleum Institute. And as far as the classification in terms of sulfur is concerned, sour or sweet, again the sulfur level would depend upon whether the crude is light, heavy, or medium. And we went through the table to understand the limits on the sulfur, which goes down as you go from heavy to light crude. And I shared some of the information of the crudes that are around and we process in our country. Coming on to the third category, so the fourth category, that is the type of crude oil, paraffin, mixed or naphthenic. In fact, I mentioned that naphthenic crude oils are quite valuable because they also are basically the feedstock for making lube base oils, which are expensive, material which you put in your vehicle, and they are also used for industrial lubrication. And then we came to this particular diagram where when you're talking about crude oil, there is nothing like a pure naphthalene, there's nothing like a pure aromatic, there's nothing like a pure paraffin. There are those components, but the majority you will find that actually it's a mixture. A mixture in the sense it's a molecule which is both aromatic as well as naphthenic as well as paraffinic. And so actually in which category do we put this in, Now, what happens is that this actually, if you look at it for a lube oil production, this is a very valuable molecule because it has only one benzene ring, but most of it, the rest of it is saturates. So actually, these kinds of, since the first ring is a benzene ring, we actually call this as an aromatic molecule, but it is less aromatic, more saturate in terms of the carbon number, hydrogen content. And this actually we came up with another definition, which is the UOPK or Watson K, which is cube root of temperature in degree Rankine upon density. And so here basically this actually determines and defines quantitatively the crude oil in terms of the paraffinicity or aromaticity. So anything greater than 12 UOPK is termed paraffinic. Anything less than 11 is naphthenic, and so anything somewhere in between. In fact, this is even valid and applicable even for hydrocarbon fractions. So if you are looking at, let's say, kerosene fraction from two different crudes, if you tell me the UOPK, roughly I will know whether with this kerosene would need any further treatment or not. I mean, this is as important as that. So if the K value, UOPK value of kerosene is high, I know that the spoke point would be high. And in that case, then we don't really have to actually do hydrotreating to saturate the aromatics. We also introduced another term called BMCI, the Bureau of Mines Correlation Index, which is actually a variable which is a function of density and mean average boiling point. And this is applicable more for carbon black feedstocks, which are used to make carbon black used in the tire industry. And that brought us to the definition of the crude oil in terms of what we call as a crude assay. So please remember that crude assay is actually something like a birth chart of crude, and it actually defines the crude in a complete way, the way the industry understands it, and we have parameters like density, API, vapor pressure, and the light end analysis, the distillation characteristics, and other properties like pour point, viscosity, wax content, asphaltenes, etc., etc., and also actually the non-hydrocarbon portion of it, which we call as impurities, but basically these are like water content, salt content, sulfur, and we'll go through all of them. So to begin with, we already introduced API. The read vapor pressure is as good as the vapor pressure you and I know. And the higher the vapor pressure, the lighter the material. So you can see that crude oil contains LPG components and propane, butane, etc. And basically, a large amount of LPG that you and I use for cooking is actually from crude oil. And why large? Almost every molecule of LPG is from crude oil, and this crude oil has this LPG in a dissolved form. So basically, the first step that we do in terms of analysis of crude oil is to actually vaporize this light material out of the crude oil, and then we analyze it by GC. So a light and analysis carried out by GC, which gives percentage right up to C5. And in future lectures, as we discuss atmospheric and vacuum distillation columns and units, this particular information is very critical to design those units, because we need to know like how much amount of LPG this crude contains, and the data is reported as shown here in terms of C1, C2, C3 content, and the ISO C4, normal C4, ISO C5 and C5, etc. Not beyond C5. So basically the LPG specification, I'll share with you what is LPG specifications. In fact, the liquid or the gas that you have in that big red bottle in your kitchen contains hydrocarbons, and the hydrocarbons are basically in the C3, C4 range. Very little C5. So there is a specification on LPG which I will discuss with you, but this LPG actually comes from crude oil. So the third aspect of the third property, the fourth property as far as the crude assay is concerned, that is distillation. And if you recall, I had mentioned that there are, four types of, basically three types of distillation data that can be generated in the lab. One is what is called as a fractionating distillation. The other is semi-fractionating or non-fractionating. And third is what we can do by GC, and it is called simulated distillation. So the first one was what we call as TBP, true boiling point distillation, where actually it's a batch distillation up to about 360 degrees Celsius, not going beyond 400, with a column having minimum of 15 theoretical plates with a very high reflux ratio 5:1. So that actually gives us a good fractionation of the various components present in the crude oil. And as a result, we get and these TBP distillation apparatuses can be actually two types of. It could be either just the reporting of the TBP curve, or it could be also preparative. What we call as preparative TBP distillation is where you can actually take the cuts physically out. So between 0 to 10%, 10 to 20%, 20 to 30%, those cuts you can take out. And then you can analyze them further to understand which molecules are present in which range of distillation. When you come to this is up to 360. If you want to go higher than 360, you cannot do it because the hydrocarbons crack. And as a result, we need to actually then go to vacuum. And ASTM D5236 is exactly the same. In fact, it is the same apparatus, same everything, only that we can now operate it under vacuum. 1 minute. Uh, Hello? Can I call you back? I'm in a meeting. Yeah. Yeah. So, so this is what it is about TBP and TBP distillation, both atmospheric and vacuum. And this is the apparatus in which we do this. So this is actually the round bottom flask in which we have a column. And then we have a refluxer from the top. This is the condenser. And these are the product coolers. And we can actually operate it both at atmospheric pressure as well as under vacuum. This is actually the good old way of doing it. In fact, you can take out samples depending upon the temperature. You can take out the first 10% or the 10 to 20%. And so this is also called preparative TBP. These actually TBP distillations take time. Typical TBP distillation can take a whole day. So actually it is very important if you want to do quick analysis. ASTM has come out with two methods called ASTM D86. ASTM stands for American Society of Testing Materials. I came up with two methods called D86 and D1160. D86 is for distillation up to at atmospheric pressure. So we don't go above 360. And if you above 360, if you need to go, then you apply vacuum. And the kind of apparatus is very simple. It's just a round bottom flask where you heat the crude and that vaporizes and distills off, and then you condense it and collect it, and you have put it in the graduated cylinder. It's a very, I mean, this is one of the first such units built to do ASTM D86. So it's easy for us to understand, but today the whole thing is completely automated. So you just have to put the sample and press the button, and you get the data on a computer. So this is how actually physically it is done. It's very simple. You just boil it and collect. On the other hand, if you want to do it under vacuum, then same apparatus, just a boiling into a hollow tube, and then it condenses. This is a condenser, and you actually suck vacuum, and you can maintain vacuum at whatever pressure you want to do, and collect the volume. So this is where actually we stopped last time. And but actually, what happens is that when you do ASTM D1160, that is distillation under vacuum, or TBP, TBP, that is ASTM D5236, that is under vacuum. The data reported by the lab is not actually the data saying that at 10 millimeter Hg absolute pressure, this is the boiling range. They actually report the data at atmospheric pressure. The reason why we actually report the data at atmospheric pressure is to not only to give a continuity. So, for example, if you do TBP at atmospheric pressure, you will stop at 360. And beyond 360, how far does it go? We don't know. Now, physically, these things may not distill at atmospheric pressure from 360 onwards. You need to operate under vacuum. But then we apply something like an Antoine equation, kind of a correction, to actually report the data at atmospheric pressure, so that people understand like what is the boiling range of this material at atmospheric pressure, and then knowing that to actually apply the right kind of vacuum to distill it under vacuum. And that conversion is actually given here. This I have taken straight from the ASTM book. Perhaps I do not know whether you can find this in any literature. But what you do is that AET is actually atmospheric equivalent temperature. That means it means a temperature at atmospheric pressure. That means atmospheric equivalent temperature in degrees Celsius. And T is the temperature which you measure. So observed vapor temperature. So suppose I measure a temperature of something like at 10% recovery, I measure temperature of 110 degrees Celsius at after 10% recovery at 10 millimeter Hg. So what I do is that I actually plug in 110 here. That's I added by 273 to make it into Kelvin, and then you put the value of A. That value of A is given by this equation, which is a function of pressure. The pressure is is in terms of kilopascals, and this pressure is the pressure at which you maintained the TBP apparatus or the ASTM D1160 apparatus. So that pressure in the kilopascal, and if suppose you have values in millimeter mercury, then you can use this equation where actually this P is in millimeter mercury. This equation is derived from here only by converting kilopascals to millimeter mercury. So the idea is that once you do distillation at in a vacuum still at let's say 10 millimeter Hg, then you plug in that value here and you get value of A, and then that value of A you use in this equation at various temperatures that you record, you'll be able to get atmospheric equivalent temperature. In today's time, actually, these machines are completely automated and these equations are programmed in there. So, in fact, what you get out of the machine, which is actually doing ASTM D1160, I mean, TBP at the vacuum, you still have to do manually, right? but this one is actually completely automated, and it gives you the values directly in terms of vapor recovery versus temperature at corrected to atmospheric pressure. So this is how you do it. The third type of distillation which people have increasingly used is what is called as ASTM D2887 or 3710, etc. The most popular, of course, is ASTM D2887, where actually it can be used either for kerosene, diesel range components or for heavy, or in fact in the entire crude oil. So basically, the principle behind the gas chromatograph is where actually the lighter molecules, they get absorbed less, so they come out first and they get detected by an FID detector, and the rest of the molecules come in that in the proportion in terms of their molecular weight. So the highest molecular weight molecule will come the last, and this is how you actually generate the data, which is shown here. So if you actually plot, a boiling point of the molecule versus retention time, so you can see that molecules which are small, they get eluted fast by the carrier gas, which could be either helium, which is normally helium, and then you actually get heavier and heavier molecules because of their higher adsorption in the column. So this is actually what is called as a simulated distillation curve. Why simulated? Because actually it is a representation. It is actually the simulation of the real thing, where the gas chromatograph, the column in the gas chromatograph, will give you large number of theoretical plates, and thereby you actually separate it out. So just remember that there are three types of distillation curves. One is the TVP, which can be done, which is true boiling point, which is actually the representation of the crude oil. And we in industry actually go more by TVP because those fractions actually tell you much better in terms of because there is less overlap. And later on, of course, if suppose you want to get things done quicker, then you do ASTM D86 or D1160. And this is how they actually compare. Because we have a 15 theoretical plate column and a high reflux ratio in TBP, so you can see that if this is again temperature versus percentage vapor, volume vaporized, you can see that the fractionation happens much better. Okay, so you have, let's say, and this is ASTM D86. So what happens is that the first vapor which comes out when you do ASTM D86, this would actually have some of the heavy ends as well. And as you go up, and then as you go beyond 50% point, then the material will also contain some of the light ends. So this is why actually ASTM D86, the curve of this ASTM D86 is actually at a higher temperature uh, as compared to TBP, and after 50 degree actually the ASTM D86 becomes lower as compared to TBP, because here you have a better fractionation. Here actually what happens is that as you distill more and more, it might actually take the light material also out of the pot still. While in TBP, if it comes out, then it gets washed down by reflux, and also it gets fractionated by the large number of theoretical stages. So please remember the structure of this graph, where if you plot temperature versus volume percent vaporized of crude oil or any hydrocarbon fraction for that matter, what you will get is, the ASTM curve will be always higher. The temperatures predicted by the ASTM for the same volume percent recovery is higher, because it actually, when it boils off, it takes some of the heavier fractions with it, and there is no way you can wash down the heavy fraction. While above 50% point, when it is boiling, it takes some of the lighter material also with it, and that's why actually, and there are methods in the which have been developed by the industry to convert ASTM D86 to TBP and vice versa, and we'll talk about that later, because the industry actually believes more on TBP, but actually ASTM D86 is quicker and faster to do. Okay. So basically, that was as far as the crude oil was concerned. Coming to the impurities part in the crude oil, and as you know, there are many impurities. And since we are not analytical chemists, so I don't want to actually get into greater detail as to how these impurities are measured. But I think for you, it is important to know that these are the impurities and what are the various techniques which are available in the industry to measure them and what do they mean. Okay, so sodium, the salt is of course one of the major impurities in crude oil and we have to remove it. So when we discuss atmospheric and vacuum distillation, I will actually tell you how we remove salt from crude oil. But salt basically is present in terms of chlorides and sulfates of sodium, potassium, basically alkaline earth metals, in which the sodium is the highest. And if you remember, I mentioned to you that this is and I mean a necessary part of the entire evil because of the fact that the crude is traded on high seas and it is actually transported from crude oil rich nations to nations which need crude oil like us. And when the VLCC, that is the very large crude carrier, when it brings crude and it down unloads the crude, the ship becomes very light and it can topple in high seas. So you have to fill up the ship, and the way we do it is with using water, seawater, from the port itself, where the crude oil is downloaded, and that seawater is filled up in the containers in the compartments of the ship, and that seawater is removed, and so some seawater remains, and that actually comes along with the crude oil. So we remove the salt, and basically now if you might ask me what are the units of salt content in the crude oil, it's a very funny unit. You would not have heard this particular unit in your life. It is called PTB. P for Patna, T for Tata, B for Bombay, PTB. And PTB stands for pounds per thousand barrel. Now, don't ask me as to why such a crazy unit, why not weight percentage, volume percentage, something like that. I don't know. But traditionally, salt content in crude oil has been measured in terms of pounds per thousand barrel, and that remains even in the 21st century. So when actually people report salt content in crude oil before treatment and after treatment, we talk in terms of PTB levels. And this is something that you should remember. These are terminologies which I'm trying to introduce to you so that you understand what is the language we speak in this industry. Um, it is actually something which needs to be removed because it can cause corrosion, and salt along with water can form emulsion and that can lead to irregular behavior in distillation. There are standard methods today. Of course, the manual methods are no longer used. We use automatic methods, and conductivity measurement is one of the best methods because you have sodium and chloride ions which are present, and they can be easily determined by conductivity measurements and calibrated against standard solutions. The other part is the sludge that you get along with the crude oil, and that is measured by a parameter called BSNW, that is basic sediment and water. And basic sediment and water is something that is a property or a kind of a property of that crude, and it depends upon not only the water content and the salt content, but also actually some fine particles of clay, ash, etc., and the material that actually get corrosion materials from the ship, etc. So these are like solid fine particles, and these are precipitated out in the storage tanks. So what we do is that, let's say in Reliance, what they do, and I'm sure the same thing is done in every refinery, is that when you pump out crude oil from the ship, you actually store it in very large tanks. So these are like large means the area of the tank would be something like equivalent to 5 football fields. So these are that big, though such a big tank, And so those tanks are actually used to settle the crude. And so we settle it for at least a week or so, and then the BSNW actually gets precipitated down. So the particles and the water and the salt, that sludge, gets precipitated down, and we remove it. So this is how, and the sediments are determined by extraction using ASTM D473. And there's a very popular method called Dean and Stark method, which is defined by ASTM D4006, by which we determine the water content in the crude oil. And this is free water content. Sulfur analysis, of course, has been researched for a long time, and this is one analysis which was done right from the time the crude oil, the refining industry took birth. And there have been many methods by which sulfur has been analyzed. But today, UV fluorescence or non-dispersive XRF are the two major methods which are used. Today, of course, all the sulfur analytical analysis methods have gone huge sophistication. Why I'm saying huge sophistication? Because we are now measuring sulfur content down to 10 ppm level or even lower. And so actually we need to develop methods also who can detect or estimate sulfur content as low as 10 ppm or lower very accurately. So that's why you see these ranges mentioned here, and those are the limitations. Like for example, colorimetry cannot measure more less than 100 ppm. By microcalorimetry, the range is 3 to 100. So between these two, they cover the entire range. Induction or lamp can go up to 0.01% to 0.4%. So 0.01% is still very high in today's context. And so basically, let's say UV fluorescence can go from 0.5 ppm to a few percentages, and so on and so forth. So sulfur content is not only measured of the crude oil, but also actually it is measured for various hydrocarbon fractions as well. As I mentioned, both gasoline and diesel, which is sold in the market today in our petrol stations, has less than 10 ppm sulfur. Okay. Coming to nitrogen, nitrogen is also now measured. This is available, mostly it is in the ppm level. And so the good old method, which you must have also learnt in your school days, is Geldal's method. But now we have microcolorimetric method as well as cumulescence detection method. So these are all automated now in terms of determining the nitrogen content, not only for the crude oil but also for various petroleum fractions. And this gives you the typical ranges of nitrogen present and sulfur present in the various crude oils. We need to remove nitrogen because it actually gives color to the products. So there was actually an instance where there was this was going 30 years ago that the kerosene used to have a very pinkish hue. There was a slight pinkish hue in kerosene, and that particular problem was referred to us at the Indian Institute of Petroleum, and we did a complete research on that to find out that there was actually a nitrogenous compound which was giving that pinkish color. And so this actually came from the oil field chemicals, the chemicals which are used in oil drilling, etc. So we actually developed a method to remove this nitrogen compound. So it gives poor stability in storage and handling. And basically, when you have catalytic processing in the, let's say, for example, if you are putting it into a catalytic reformer, the catalytic reformer catalyst can get affected if you have high sulfur and high nitrogen. Coming on to the other characteristics of the crude oil, asphaltenes is something very important. And because actually asphaltenes is something that you can't really do any value addition. If you have to do value addition to asphaltenes to convert it back to gasoline and diesel, a large amount of hydrogen and energy is required. So if you have a higher asphaltene content in crude oil, to that extent that crude oil has lesser value for you, okay, in terms of making profit. So these asphaltenes, as I mentioned earlier, these are polynuclear condensed aromatic hydrocarbons having high molecular weight. And the way we do it in the industry is that we actually subject the sample to what is called as heptane insolubles. So we actually try to, there's a certain method covered by ASTM. So you take a certain ratio of heptane to the sample, and whatever dissolves is fine. Whatever is not soluble is asphaltenes. So these are insoluble so asphaltenes are insoluble in heptane. So in many of our discussion in the industry, we ask how much is the heptane insoluble. What exactly we are referring to is the asphaltene content. Okay, and both asphaltenes and there's another characteristic called carbon residue. So both asphaltenes and carbon residue indicate the extent to which the heavy hydrocarbons are present in the crude oil. The ash content, of course, generally crude oils are very, very low in ash, unlike coal. So coal, when you burn, it could be even 20, 25. Indian coals can go even up to 35% ash. But crude oil, by definition, have very low ash. The ash that you will get actually when you burn off crude oil is primarily because of the metal content, because the metals they don't burn off; they will just remain as a solid form. So that is depend. So that is another way to determine like how much is the metal content. Any carbon and hydrogen, sulfur, nitrogen, all those hydrocarbons will burn off. Anything with metal will just remain. One way to actually determine the asphaltene content is also by measuring characteristics of the crude oil called carbon residue. And this is actually just in a layman's language. What carbon residue means is the carbon that is left when you pylize the sample. That means you take the crude oil, measured quantity of crude oil, let's say 20 ml, in a platinum crucible, and you slowly heat it up. So slowly over a period of time, you are actually decomposing the hydrocarbons. So whatever evaporates will evaporate, and ultimately whatever the heavier hydrocarbons are there, they will crack, and they will actually make a carbon deposit on that. And that deposit, if you weigh, that is actually the carbon residue. So generally, this particular experiment takes about 5 to 6 hours, and it is called as Converson carbon residue. The Converson is the name of the person who actually came up with this method, and this is now standardized by ASTM D189. But this is a very lengthy method. I have done this particular test myself in the Indian Institute of Petroleum when I was in EIL. And yeah, it actually almost 5 or 6 hours it takes, because you need to actually be very patient with regard to the pyrolysis that you do. Now, of course, there's a very quicker method called Ramsbottom carbon residue. In short, it is also called as RCR. Conversion carbon residue is called CCR, C for Calcutta, CCR, and Ramsbottom carbon residue is called RCR, and that is covered by 524. And today, of course, even this has been completely automated, and we have instruments called MCR, that is microcarbon residue, called ASTM D4630. So now you have actually very small tabletop equipment or machine that comes in, where you actually open the lid and you put the sample, weighed amount of sample, and then you close the lid and you press the button, and about half an hour, 45 minutes, it will tell you the carbon residue. And that is called as a microcarbon residue. Generally, the microcarbon residue values are same as condenser carbon residue. So that is how actually we determine the asphaltene content. I mean, what people have done is, in fact, this particular graph I have taken from straight from the ASTM book, which describes ASTM D189. So if you see on the y-axis, I have plotted the Ramsbottom carbon residue, and on the x-axis is the Conderson carbon residue. And this actually has a relationship. So what we do is that if suppose CCR takes more time, then we get an RCR done. And this was I'm talking about in good old days where the MCR machine was still not invented. And so we get the RCR done, and then from this graph we actually see like what will be the corresponding CCR. As you can see that both of them are equal at 20. So roughly about 20% RCR, it is equal to 20% CCR. But below that, actually the values are quite different. So the RCR values are generally, higher as compared to yeah, they're lower as compared to actually the CCR values. So this is as far as the characterization of the crude is concerned in terms of the heavier components. Another important characteristic of crude oil is the acid number. And generally, why this is of interest to the industry is because if you can actually process high acid crudes, these crudes come at a lower cost. And if you're processing something like the kind of quantities we process in Reliance, almost like 64 million ton. So even 5% of that, roughly about, let's say, 3 million ton. If you can get high acid crude, there's a lot of money to be saved. I mean, today actually the crude oil prices are above $80 a barrel. I would actually encourage you to look at crude oil prices on a daily basis because that will actually tell you how the volatility of the crude oil prices are there in the market and what are the variables which actually govern crude oil prices. So TAN, which is actually total acid number. Total acid number means total acidity, organic acidity in the crude oil, which is both carboxylic and naphthenic acid, and also if any inorganic acid is present. So the light organic acids, when they vaporize, they can cause corrosion to the carbon steel metallurgy. While naphthenic acids are present more at a heavier hydrocarbon range, and they are very nasty. I mean, they can actually drill a hole in your pipe. So we have to be very careful about the quantity of these acids present in the crude oil. And the speciation sometimes becomes difficult, but there are methods by which you can analyze which kind of naphthenic acids are present. Generally speaking, we try to limit the TAN content of the crude oil less than 1 milligram of potassium hydroxide per gram. I mean, what do you mean by milligram of potassium hydroxide is there is a certain method, a titration method by which you can determine the naphthenic acid or the carboxylic acid content in the crude oil. And that is measured in terms of the amount of KOH, a milligram of KOH per gram. So we try to limit it below 1 so that there is no accelerated corrosion of the refinery equipment. And these are some of the high acid crudes which are traded worldwide. And you can see the origin. Basically, Venezuela is very rich in crude oil, but most of the crude oil in Venezuela is either heavy crude or high TAN crude. In fact, this Mary crude is a very famous crude. In fact, in Reliance, we actually buy a large quantity of this Mary crude. Merlium crude from Brazil or Kyoto from Angola. And of course, even in UK, we have certain crudes which are quite high acidic in nature. So you can see the acid number here. And this is the API gravity and the sulfur. So, I mean, you can see that even for an API of 27, 28, we still have a high acidity. So we cannot say that, if it generally in this graph, you can see that lower API, that means heavier crude, is actually having TAN, but not necessarily. Okay. So TAN can happen even with light crudes or heavy crudes. Then coming on to the metals, the ones which actually produce ash when you burn crude oil. The metals which are generally present, generally means all crude oil would have at least three metals: nickel, vanadium, and iron. But you can have other metals also like arsenic, lead, and depending upon the crude source, you could have even heavy metals like copper, cobalt, chromium, strontium, but these are rare actually. And mostly, actually, if they are there, they might come from the drilling mud actually, and mercury and selenium. So basically, these are the metals that might occur, and there are various instrument methods. In fact, the industry has installed some of these very expensive equipment like ICP can cost you or something like 2 crores of rupees. But it's a very accurate machine by which you can get the metal content like vanadium, nickel, iron, copper, etc. Uh, there is no limit of detection actually. It depends upon how you prepare the sample and how do so there's a lot of expertise required to actually use these instruments. So coming to the end of this, this characterization of crude oil, uh, I had shown you a glimpse of what is crude assay, but in the industry, there are three types of crude assays which are actually done. Crude assay takes time, okay, and the positive part is that there are labs which actually do these crude assays, like we at the Indian Institute of Petroleum, where I was there earlier, we used to get a large amount of crude oils from all over the country for doing crude assays. And those crude assays get published. So one can actually go with that rather than running a crude assay on a new cargo. But generally, what happens is that, as I told you earlier, that the wells, when they deplete, the crude assay can change. Okay, and so there are companies like very much in Reliance where we go by standard crude assay, but we do some preliminary testing of a new cargo which arrives, and some 5 or 6 parameters are measured, and that actually we have identified which are those 5 or 6 parameters which actually define if there is any change in crude assay. And if those 5 6 parameters are different, one of course is sulfur, the other is CCR, and if they are different, then actually we run a complete crude assay. So what are these three different types of crude assays? One is called as a preliminary assay, which is actually just to get just a rough idea as to what this crude oil is. So the objective is to just check consistency of crude supply and have a preliminary indication. So this is what I mentioned. These 5 or 6 parameters that we estimate. Because of confidentiality, I cannot tell you these parameters, what we actually do when a new cargo arrives at Jamnagar. But that is just to check the consistency. So that is the preliminary assay. And this is just without any TBP or ASTM, etc. Then comes the short assay. This is actually a bit more than the preliminary assay. So this is the objective is the processing of this crude oil in a fuel refinery, and mostly actually this is done to determine the pricing. So if there's a price negotiation to happen between the supplier and the user or the consumer, then actually the short assay is done. And what it means is we do a complete crude oil characteristics. We determine all these trace metals, sulfur, nitrogen. We actually run a complete TBP assay as well. And sometimes we do actually the yield for the various straight run products and their characteristics. This is actually a short essay. It is basically the kind of data that I just showed you earlier. So the complete TVP, complete crude oil characteristics like pour point, cloud point, whatever I had actually listed earlier, and also the impurity levels. But the other one, the third type, which is of course very detailed and it costs a lot of money. And basically, this is done in by this is actually got done by people who produce crude oil, like ONGC, Oil India Limited. They are actually producers of crude oil. They produce crude oil, and so they would like to get their crude oil benchmark in terms of what exactly is the value of that crude oil for them to understand. Okay, and so for that we do a complete detailed essay in which let me actually go through the scope and then I'll tell you the objective why this detailed essay is done. What we do here is that we run the complete characteristics of the crude oil, as I mentioned earlier, the micro constituents, etc. But then when we do the TBP, we actually do a preparative TBP in which we actually withdraw cuts, okay, and both in the atmospheric and the vacuum range. And each of these cuts are subjected to detailed component-wise analysis to the extent possible, both the light and the hydrocarbon portion. And so each and every cut is reported in full detail. And to the extent possible, detailed characterization of long and short residue. So you have the complete fingerprinting of this crude oil. And I'll show you a typical data in the next slide. But why do the oil companies require this data is basically if you have to design a new refinery, let's say we actually design a new refinery. The way we design it, we actually design it flexible enough to be able to process a light crude and a heavy crude. And so basically, when you design a new refinery, something like 5 or 6 different crudes are actually identified, which will provide the full flexibility of that refinery in terms of its processing. And for that, we need this complete data so that we know what kind of fractions we'll get and how much quantity and like what are the impurity levels and what are the hydrocarbon types which are present in each of these fractions so that the other units, the secondary conversion units like catalytic reforming, fluidized catalytic, like the feed to the FCC is the vacuum gas oil, right? So the vacuum gas oil goes into the FCC. So what is the characteristics of that vacuum gas oil? As you can see, this is detailed component-wise analysis right up to vacuum distillates. And then based on that, we can do the optimization of product yield. So suppose we are processing a new crude and we would like to operate the refinery in order to maximize the value from that crude, then we need to have the complete crude assay and so on and so forth. So it's for modeling and simulation and also for marketing for the oil companies to market this crude. I'll tell you one very interesting incident. Actually, when we were doing this crude oil assay for ONGC, we identified that there was a particular crude. I cannot name that crude, but there was a particular crude which had pretty high content on normal paraffins in the kerosene range. And so actually we told ONGC that this is a valuable crude for a certain refinery which is making LAB, linear alkyl benzene, which is a detergent intermediate as I told you. And so this particular refinery can pay more for this crude oil because they can make more money by processing this crude. And so basically ONGC got the idea and they negotiated that refinery and got higher value for their crude, for that particular crude. So this is how any other refinery which is not making LAB will not actually be able to get value because it's selling that kerosene as a fuel. But this particular refinery was taking a C9, C13 fraction of the out of that kerosene and separating out the normal paraffins. And that normal paraffins they were then dehydrogenated and alkylated with benzene to make LAB. So higher the normal paraffins, the more LAB yield they get. Okay, so that is why the value was more. So these are this is similarly, like for example, if you're talking about naphtha. Now, if the naphtha fraction, which is actually boiling in the range of 110 to 160 cut, has higher content of naphthenes, then actually, if you put that feed into a catalytic reformer, you'll get more aromatics, and we'll learn all this later. But just for now, please remember that there's a technology in the refining industry called catalytic reforming, which produces gasoline. and also produces aromatics. So basically, this is one unit which actually manufactures aromatics, and that is done by dehydrogenation of naphthenes to aromatics, and hence actually it becomes very important for us that this particular feedstock is actually this characterization is done completely. And this particular chart tells you what exactly I was talking about so far. It looks a very busy table, but let me slowly walk you through it. What you see actually on the second column is the cut range, cut temperature. So these are actually the cuts that were actually obtained. So this cut, cut temperature. So this is actually up to 50 degree. This is up to 75 degrees. So this stream number two contains all the components between 50, boiling between 50 and 75 degrees Celsius. This contains everything between 75 to 100. This is the cut temperature. So beyond that, you don't go. This is from 100 to 125, 125 to 150, and so on and so forth. So this is how you do a preparative TBP. Okay. And this is right up to 370. So this is TBP at atmospheric pressure only at 760. We determine how much weight percent these fractions are on crude. So 39.4% of the crude is boiling above 370, while the rest of it is distributed like this. Then the density of each of these fractions, as you can see, density will go up as you go up on boiling point. And this graph is very important. We actually plot density versus temperature. And once you know the once we know the temperature, and you know the density, you can calculate Watson K, UOPK, right? And so that is how we actually determine the paraphenicity as well. So this is the last column that you see is actually the UOPK, which is calculated, and this calculation is based on this density and this temperature, converted to the appropriate units. This density is converted to API, and then these are the aromatic content which has been determined by gas chromatography, and the saturate content. This is the smoke point measured, and the higher the smoke point, the less is the aromatics. So similarly, the freezing point and the freezing point would depend upon, of course, the fraction. So as you go up, the freezing point increases. Aniline point is another variable which I had asked you to define, but this is actually a measure of the aromatic content in the feed. The lower the aniline point, the lower is the aromatics. And as you go up, actually, you get higher and higher aniline point. Diesel index, this is actually some measure of cetane index or cetane number. Sulfur content is measured. As you can see, as you go up, the sulfur content keeps on increasing. There's some similar is the viscosity, both at 40 and 50. So in our industry, we actually end up doing viscosity at least at two temperatures to determine how the viscosity changes with temperature, and then the UOPK. So this is actually what we call as a detailed crude assay, and not everything is reported here. Actually, there's when you do a GC, you get a very large amount of data, so that is all reported. This is just the final slide in terms of crude oil and various methods that are used. AAS is atomic absorption spectrophotometer. ICP is the induced coupled plasma. GLC is the gas liquid chromatography. So you can people use even NMR, that is your the nuclear magnetic resonance, basically to determine. This is a very powerful technique by which you can determine each and every molecule to the extent possible. So you can see that how various methods are used as we go down from gas to the residue in a crude barrel. So that's all I had actually as far as characterization of crude oil is concerned.